Okay, so we'll cover digitally controlled DC-DC converters. And so if you look at the limitations of analog controller, the compensation network is usually we design using RC network and op-amp. So we know that let's say we are operating at 1 megahertz or so, your bandwidth requirement will be 100 kilohertz, roughly 1/10 of that, and you can estimate the values of compensation capacitor, and we already looked at it. It was coming like order of 50 picofarads or so, and we require two capacitors because we have two zeros here and one integrator. So roughly like total capacitor, if you look at maybe order of hundreds of picofarad, which will occupy a lot of area. So that's a one limitation. I mean, obviously it's very area consuming. Then the discrete nature of compensator makes it difficult to track any variation. So I mean, even though you can change the values of resistor, put a RDAC or so, but there are certain limitations with that also. And if I want to change, let's say, capacitor, then you may require a very large switches because you don't want to add ESR to the capacitor in series with. So changing the capacitor is not a like a good option. We can change R, but there will be some limitations with R as well. Let's say you don't want to change the gain, but you want to change only location of the zero. Then in that case, when I say gain, it's a proportional gain, the ratio of R2 over R1. So then it may affect both actually, because you cannot independently tune zeros and gain. So that's another limitations. And then it doesn't provide reconfigurability. When I say reconfigurability, that let's say you have designed your converter for 1 microhenry sort of inductor and 10, let's say 10 to 20 microfarad of capacitor. Now if somebody puts, let's say 4.7 microhenry, most likely your converter will become unstable because you haven't designed your compensation network for those values of inductors and capacitors. So mostly when you design, you simply look at the tolerance, which is plus minus 10 to 20%, and you design for that. But if you have to cater to, let's say 200%, 300% kind of a variation in L, then it will not work unless you change the your parameters, compensation parameters, which is basically your gain and location of your zeros. So this table is showing the basically how your I mean the tolerances and the pole. When I say pole, it's omega naught actually, the resonance pole. So 10 micro Henry and 4.7 microfarad. This is the value, and then you have a 20% tolerance, let's say, so 29, and then it may become unstable. And if you have designed for, let's say, these values, which is, so roughly you have designed for 15 kilohertz kind of value, and if it varies to, let's say, 23 kilohertz, and which means from here to here it's roughly 50% variation, you can say, then it may become marginally stable or unstable, which means, I mean, it may become completely unstable, which means you will have lot of ringing, or it may settle within few cycles, but you will have still some ringing. So settling time will be more, and overshoot, undershoot will also be more, which may be unacceptable for the system which you are powering to. So which means like maybe 20-30% variation may be okay, but the moment you go plus minus 50% kind of variation, it becomes very difficult to stabilize these converters. So then I mean, to address those issues, we go to digital control DC-DC converters. So unlike the analog solution, digital control can provide flexibility of tuning filters, because everything is digital here, you can program easily. So the coefficient can be programmed, and you can easily change the gain and location of your zeros. And it's a fully integrated, so no off chip compensation, means let's say your compensation network in a Paltronics, they usually design for 100 of kilohertz kind of, because their power fetch is very large, so they cannot operate at order of megahertz, and their current requirement might be like more than 10 amps or so. So in that case, they mostly require off chip capacitor, because this may be order of nanofarads, and it's difficult to put on chip. So they simply use a controller chip and put your compensation network will be around that. So you can assume that your op amp is inside the chip, but the RC network around that will be off chip. So that based on the L and C they choose, they can choose the RC values. So with the external, that is a flexibility that you can change the compensation parameter, because now you can simply replace the register with a different register, but then you have to pay something, because off chip means it's a cost is involved here, and it will take area on the board also. So but if you look at digital, then it's fully integrated. You don't require any off chip compensation. Only off chip component will be your L and C filter. Obviously you cannot integrate that microhenry and microfarad kind of capacitor, so it has to be off chip. Then the loop can be designed to adapt any changes in both off chip and on chip components due to aging process, temperature or vendor selection, which means let's say I have put an inductor and capacitor externally, and I know that tolerances may be plus minus 20% in both, and then with the temperature and aging, that may be even worse. Okay, and if you remember, we talked about this inductor, basically the characteristic with load, it starts reducing, and 70%, below 70% it goes, we consider at it's saturated. So if you consider everything, the variation may be easily 50% or so. And if you haven't over designed basically or over compensated your DC-DC converter, then it may become unstable. And one thing you have to remember, whenever you over compensate anything, it will be slow in nature. Okay, because now you are looking for higher phase margin, and that you can achieve by reducing the bandwidth only. So you have to pay for something if you want to overcompensate. So but in digital, you can basically measure all the parameters digitally and tune your parameters accordingly. So dynamically you can change if there are any dynamic variations in your, let's say, compensation parameters or external components. Then another advantage is easily scalable with the process. So let's say you are working on 180 nanometer CMOS process. Now you want to move to 65 nanometer CMOS. So you have to redesign everything. Okay, because I mean, for the same size of the transistor, all the values will change. Your RDS will change, your GM will change. So which means your gain and everything will change. So you have to redesign, and your R and C will also change, because it's a different process. So the sheet resistivity and the capacitance per micron meter square, the capacitor density, everything will be different in different process. So you have to almost redesign everything from the scratch. You may use the same topology, but ultimately you have to enter the transistor size, everything. It's a time consuming process. But in case of digital, you have to take the Verilog code or VHDL code, synthesize it, done. It doesn't matter what process, the Verilog code will not change, because Verilog code is nothing but behavioral. Okay, and when you synthesize it, it simply picks the logic gates from that particular process library, and it will synthesize and convert your code into circuit. That's it. So you are done. So it's easily scalable across the process. So how it works? So what you have a error voltage, just like in the analog. Now you have to digitize it, which means you have to put analog to digital converter. Now you get the digital code. So this is nothing but your error, which is represented in binaries, okay, 0 and 1, and then you have the same PID, but it is digital now. Earlier we had analog, which is continuous time. Now you have digital compensator, and then this will give you again the control code, which we were calling VCTRL in analog and comparing with RAM. Now you need digital PWM here. So that's a difference. So everything is digital here, no analog component except this A to D converter. The moment you get the digital code, everything has to be processed in digital, and then this will eventually give you VPWM. So from VERR to VPWM, there should not be any difference between analog and digital. In between, how you process, that is, if you look at a black box. So as long as your end results are same, you don't care whether it's implemented in digital or analog. So there are certain constraints on ADC. So obviously the main thing is resolution here. So let's say V out is 1 volt, and if regulation specification is 0.1%. So which means you require accuracy of 1 millivolt, okay, and this will make you to design a ADC of 10 bit, okay, 10 bit corresponds to 0.1%. So now then conversion rate depends on PWM switching frequency. So let's say I am operating at 1 megahertz, and which means your code should be updated every cycle. If there are any changes in let's say low transient appears, then you should be able to respond right away. Otherwise, the moment you have a delay, then it will degrade your transient response. So which means your code should be ready, the next code should be ready when the next PWM cycle appears, or in most of the time for transient, in order to cater to transient, different transient response, we usually design asynchronous basically kind of control, where it can respond right away during transient, but in the steady state it will be synchronized with PWM. Just like you can imagine, it's a hysteretic versus your voltage mode control. So designing a 10-bit ADC at a, let's say, 1 megahertz or beyond frequency, it's not easy. I mean, it's going to take a lot of area, a lot of power. Okay. So, and the main thing to go to digital is we want to save area, and we want to save power also actually here. If you are not able to save these two, then I mean ultimately we are looking at a benefit of going to digital. So if we are not able to save area, then it's not benefiting us and doesn't make sense to go to digital. So obviously if we make a slower ADC, then what will happen? We are forced to reduce our bandwidth, otherwise the pole which will be occurring due to slower ADC will start interfering with your loop and your phase margin will degrade. So there are different ADC architectures which try to basically overcome these limitations, where we require 10-bit kind of ADC. So we'll go over it and see how we basically fix these issues. So ultimately what I require is delta V is 1 millivolt. I don't require I mean, that doesn't mean that you always require 10-bit ADC. So when the transient, low transient comes, I mean, how much voltage will be deviated from your steady state? Maybe 50 millivolt, 100 millivolt, not more than that. So you don't need a 1 volt dynamic range here. Even if you are regulating at 1 volt, that doesn't mean, and you want accuracy 1 millivolt. But if you look at the dynamic range, which means the deviation from 1 volt, it may be plus minus 50 millivolt or 100 millivolt max, depending upon how big capacitor you have put. Okay. So the maximum undershoot overshoot you are expecting, you only want to resolve that. So your range is limited here. So what you do, you truncate your basically range and still achieve 1 millivolt. So 1 volt versus 1 millivolt, 100 millivolt versus 1 millivolt. Now you require only 7 bit, correct? So that's what we do usually. I mean, so the example is like, let's say window size is 6 millivolt, which requires only level of 3 bit. So depending upon compared to 10 bit. So it all depends how much you are expecting from there. So and then another, so and also, I mean, nobody is saying that I should keep these steps linear. So whenever I am near to 1 volt, I can reduce my step size, let's say 1 millivolt. When I am away from 1 volt, then I can increase that step, because that time I am responding to transient. But this regulation or accuracy requirement is in steady state. So in a steady state you are regulated at 1 volt. So around 1 volt, when your basically when your error is 0, then keep your resolution 1 millivolt, and when you are deviating from away from the error, you can keep increasing the step size. So let's say you can do 1 volt, 1 millivolt, 2 millivolt, 4 millivolt, something like that. Then in that case you don't even need a, let's say we just took an example, if you have to cater plus minus 50 millivolt, then you may require 7 bit. Now if I use a non-linear steps, then I may be able to do in 3 or 4 bits only. So this is linear steps, and now this is non-linear. So when you are near 0, you can say step size is less, and then I keep increasing. So non-uniform quantizer actually. So and I know in steady state I will be here, my error will be 0. So I can be regulated within 1 millivolt, and when I am going away, I know this is steady state is not here. This is only during transient. So during transient I don't care actually, because I know I'll be in any case deviating 50 millivolt or so away from your regulated voltage. So even if you use a large step, it may not matter that much. So that's the advantage of using non-linear quantizer or non-linear ADC, and I have given a reference for this paper. If you want to read, you can go over it. Then another architecture is this is based on oscillators, what we call ring oscillator actually. So, and ring oscillator is nothing but it's like you have inverter and 3 odd number of inverters connected, input and outputs are shorted of that chain actually, or you may have a differential delay cell also. So people who are taking PLL, they know, and or if you are taking PLL in future, then you will understand better what exactly the VCO is. So what is happening here? This is nothing but your GM cell, and in the GM cell these loads are current mirrors, but those current mirrors are replaced with VCOs. So any difference between V out and Vref, so let's say I am regulating my output to Vref, so any difference will generate a difference in current. So let's say V out equal to Vref, so both VCOs will see the same current, and if they are matched, their frequency will be same, F1 equal to F2. Now if I count, let's say these two with a lower frequency, so let's say this is operating at 100 megahertz or so, and in 1 megahertz reference cycle, I can count the number of cycles of this. So 100 cycles each will give if they have same current. Now if there is any difference between the two, the current will stir and it will generate a difference in frequencies. So, and correspondingly you will get a difference in counter output, and the difference will give you the digital error. Okay, so this is a very simple ADC, you can design it very low power actually. It does not require any capacitor, resistor, anything actually, quite simple. The only problem is the linearity, because these VCOs are not perfectly linear with this basically variation, I mean with the when versus current or voltage actually. So this is not exactly the VCO, but it's a CCO actually, current controlled oscillator, because input to these VCOs is current. So they may not be perfectly linear, but we are looking only for the plus minus 50 millivolt kind of a range. So within that range, you may get a decent linearity, which will be okay for your application. So that was using voltage controlled oscillator. The same thing you can do with the delay line. So the delay line is nothing but you can think about a flash ADC. So this was a flash ADC, where you have a multiple comparators and compare with the references, and you get an output code. So if you, I mean for all the comparators where the input reference input is below your basically the feedback voltage or output, then you will get a one code. Okay. So I mean assuming that your positive is getting the input and negative is getting the reference. Okay. So if negative is lower than positive, you will get 1 and rest of them will be 0. So your code will always be like some comparators will be 1 and rest of them will be 0. So wherever this transition happens, that will change you where exactly your output is lying, at what reference. So the same we apply concept apply here in delay line. So what you are doing actually, so these delay lines and delays of these are function of your input voltage. So if this voltage changes, then the delay will change, and you are sampling this delay. So this is a D flip flop and this is a clock, and clock edge is fixed, and so whether your D is nothing but is a delayed version of your test signal. So let us say you apply a clock here and you apply a sampling clock here. Now each delay will give you the edges will be delayed with respect to your sample clock. So depending upon whether it comes early or late, this flip flop will give you 0 or 1. So if this edge comes after this clock, then it will be 1. If it comes before that, then you will be sampling, no sorry, if comes before that, D comes before your clock edge, then it will be sampling 1. If it comes late, then you will be sampling 0. Okay. So the same thing what you are getting in the flash, you will get the same thing here also. So and the code will change, and these delays are function of input voltage. So, it will generate different codes with respect to different input voltage, and then you can decode that and convert into binary, because the output code is not binary here, just like in the flash it is not binary coded signal. So, you can convert it to binary coded signal using encoder. So, then you can register those, and so and this is same delay line which is sampling both reference and input. So, one cycle you reference, you register that reference digital, and that's not going to change every time you cycle that reference. But the reason you want to sample every time, because the delays might change because of PBT. So, let us say when I have sampled now, and at that Vref this is giving some delay, and next time when I am sampling the temperature might change. So, this will give a different delay, and if I do not sample it again, my code will not update. So, you will get a different error for the same value of input voltage here. So, it will keep calibrating basically. So, it will keep updating the reference code based on any variations in the delay cell. That is why you are sampling both input and reference. Okay. So, then another option is you can do this, you can use two basically delay lines. One is the, so the problem with this was actually when you are sampling the input, so you are using common delay line here, which means let us say I have sampled the reference, and next time when I am sampling the input, if the delay is changed between those two samples, then it will give me error. But here you are assuming that when you sample the reference and after that when you sample the analog, the delay is not changed, but in between the time when you sample the Vref and then now I am sampling the analog voltage or input voltage, which is nothing but feedback voltage. So, if there is any change happens, let us say due to temperature, mostly the temperature is something that will dynamically change here. So, in that case you will get an error. So, what we do, which means if I keep continuously sampling the Vref, then this problem will not happen. So, now I need two delay lines. So, what I am doing here, so one delay line is sampling the Vref, other delay line is sampling the output voltage. So, you can see here there is a this is V out and this is your Vref. So, the difference of this will get converted to voltage and generate this bias voltage, and same thing will happen here. So, the way it is done, because so that you can get a same common mode voltage actually. Okay. So, these two are just a replica of the same, and so when your these two are ties, which means for the zero error or Vref you get some voltage here, and then when you have a difference here you will get something else. So, when V out becomes Vref, this V bias ref and V bias out should be same. Then after that you apply the same thing, okay, encoder, and then register your output. So, that will give you the error code, and after that you pass it to your PID, digital PID.